The plan for today is I'm going to recap a quick overview of what we went over last week, the geometric preliminaries. I'm not going to go into details. I'm just going to talk about what we have talked about last week. And then there are some parts that I missed in these geometric preliminaries. Like we have talked about the sine law, cosine law, but we haven't mentioned the sine law, which is related to the cross product of two vectors. And also planes, plane equations. How do we represent planes in 3D space, for example? We also did not mention these things. And also half spaces or half planes. How do you represent a half plane, a three-dimensional half plane, for example? What do you need to represent it? And then I'm going to as an exercise to test our knowledge on these geometric preliminaries, I'm going to do an exercise which is going to try to find the intersection between a 3D line and a triangle, a 3D triangle. So this is a practical problem that you can face in a computer graphics application, in an interactive computer graphics application, in which the user clicks on a point on the monitor, and clicking on this, basically, you are, based on the perspective projection that you are using, you are defining actually a line towards the three-dimensional space that you are looking at. Imagine there's a three-dimensional interactive program that, like a 3D first-person shooter game. You're looking into a three-dimensional virtual world through a camera. And by clicking on a point on this camera, based on the perspective reference point, and this point you click on the camera defines a line segment, and actually the extension of this line segment towards the three-dimensional virtual world defines a line or a half line. And most of the time you may be interested by clicking on this monitor, we may want to select certain three-dimensional objects in this virtual world. So we may want to find that, or and if our 3D virtual world is made up of triangles, we may want to know which line segment this triangle intersects. Now I'm going to simplify this problem. In order to do this efficiently, we may need certain index structures to avoid testing our line segment with all the triangles in our scene. Okay, our scene may contain 1 million triangles. We don't want to find out whether it intersects with every one of them. So we basically usually employ a three-dimensional index structure to filter out certain triangles that are not supposed to intersect. But today the problem, I'm going to simplify the problem. Just given a single triangle in this 3D world, and maybe this is the triangle that you found that you're intersecting with. You found the intersection test turn out to be positive, but you are wondering exactly at which point you're intersecting this triangle. I mean, if it's a big triangle in your scene, like this, and if this is your perspective reference point and this is the point you clicked on your monitor, this may want to find out the exact detailed coordinate of this intersection point xi, yi, zi. Okay, so at what point we intersect this triangle. So the problem becomes, given 2 points, x1, y1, z1, and x2, y2, z2, which defines our line, and given 3 coordinates, which are the endpoints, vertices of our triangle. XC, YC, and ZC. Find the intersection point xi, yi, zi. So we are going to try to solve this problem using the geometric preliminaries that we have seen last week. And today we are also going to see some, we may need to learn, we may need to know plane equation as well. So I'm going to go over plane equations for that. So Also, I'm going to recap what we have covered last week about convex hulls, the ON cube solution that we have found, and we mentioned degeneracies and robustness issues. And today I'm going to talk about an efficient solution, which is also explained in the book, which is an incremental solution, which solves the same convex hull problem in ON log n time. And we are going to go over the correctness of this proof. Then we are done with the first chapter of the book, and we are going to start the second chapter, which is line segment intersection. And in that problem, our goal is going to be find an efficient algorithm to find the intersecting line segments. Given n such line segments, trying to find out which ones are intersecting and at which points they intersect. Okay, so this problem, line segment intersection, practically it appears in, for example, GIS applications. Like, for example, you may have a road map. Your roads may be represented as line segments following each other. And you may have a river map, okay, which are also line segments. And these are usually in GIS applications. These two information are stored in layers. Okay, you have a road layer, you have a river layer, maybe you have a forest layer. Forests are not going to be represented by line segments, but they are going to be represented as subdivisions of the plane. So sometimes you may want to have such queries like, find me the bridges on this map. So finding a bridge means that you need to find an intersection of the road with the river. Okay, so this problem returns to mathematically a simple problem of if you represent your roads as line segments and your rivers as line segments, you need to quickly find all the bridges, means that quickly find all the intersection between two sets of line segments. And we are going to again simplify the problem to say that, okay, instead of having two different sets, roads and rivers, the question, if we can answer the question whether given a single set of line segments, whether if we can find intersections between them efficiently, then we can solve the other problem efficiently as well. All we need to do is just check whether the two intersecting line segments come from two different layers. You only need to do this additional check to solve the original problem. So we are going to discuss an algorithm which is going to be able to compute the intersecting line segments in n log n time. So, but you may directly object to this m log n because what if n square line segments intersect? Okay, how can you guarantee an n log n algorithm? And so the algorithm is not going to be n log n actually. It's going to be m plus I log n complexity algorithm. So I is the number of intersections. So such kind of a time complexity is called output sensitive complex, or this is an output sensitive algorithm. If the number of intersections, this I is the number of intersections between line segments, and they can be order of n square. At most, okay, there may be n square intersections. So if there are n square intersections between your line segments, you are going to have n square log n complexity here. But if number of intersections I is much less than the number of line segments themselves, okay, then you are going to have an efficient. You are going to have an n log n algorithm instead of an n square one. So usually, if we are given short line segments, and like we are given millions of such line segments which are short. In the general practical map intersection problem, we are not expecting this many bridges. Only the roads and rivers intersect only at certain points. So we expect this now I to be a small number. Okay, if it's a small number, then our algorithm is going to behave as if it's an n log n algorithm. The I is going to be, we'll be able to neglect I. Okay, so that's the plan for today. After we are going to introduce, we'll be able to achieve this n log n complexity with an algorithm type called plane sweep algorithm. Plane sweep is a general algorithmic technique to solve geometry, computational geometry problems. It's not specific to line segment intersection. You can, for example, use plane sweep to find the closest pair of points. Given n points, if you're asked to find what are the closest pair of points in these n points, you can use a plane sweep algorithm to answer this in n log n time, or n log n time. The brute force search is going to take n squared time, and usually, since log n is really small, log n is growing really slowly, n log n is much more closer to a linear complexity than n squared. So n squared grows much faster than n log n, so an n log n algorithm is usually desired if you have millions of points. The difference, the running time difference between an n log n algorithm and n squared algorithm may be huge. Okay, so, yes?
O zaman biz çalıştırırken belki de algoritma hiç durmayacak. Yani çünkü n squared diye çok büyük bir şey. Bilemeyeceğiz.
Exactly. Exactly. So if based on certain input. So the question is, if it's output sensitive, it may sometimes have n squared complexity based on the number of intersections you report, and it may take very long to report these intersections. But if there are many intersections, and if you want to learn all about them, there's nothing you can do. Okay, I mean, if you want to learn all of these intersections, you should expect to wait long. Okay, so that's what output sensitive is. So this, after we discuss this plane sweep algorithm, which is an easy algorithm to describe. But when we handle the degeneracies, it's going to be, handling degeneracies will make the algorithm a little bit more complex. And an implementation of this plane sweep algorithm for line segment intersection is really difficult, especially implementing a balanced binary search tree which has line segments as objects in it. I mean, you can have a binary search tree to sort points or single integers, but when these are line segments, how are you going to compare two line segments, which one is on top of the other? I mean, these things is going to make the algorithm, some practical issues are going to be difficult to implement, but we are going to discuss these things. And if time permits, I'm going to start a new data structure called Doubly connected edge list, which can be used to represent subdivisions on a map or on a plane. If we have certain areas, how do you represent areas? They may be overlapping areas, disconnected areas, like forests, for example. You may have forests on a map. How do you represent these forests, these regions, digitally on computer? Okay, so we are going to see a data structure called Doubly connected edge list, which provides us efficient query mechanisms. If the user clicks on a certain point on this map, for example, we may know this point belongs to this area. Okay, and you may, for example, based on this point, you will be able to walk along the edge of this region that contains the point. And that's my plan today. And next week, we are going to, given two doubly connected edge lists that represent two different map layers, next week we are going to see an algorithm to find the intersection of these. This is called the map overlay problem. Overlay of two layers. Where do they intersect? We are going to see this next week. Okay, so let's start with recap from last week. So what we discussed last week was we discussed some geometric objects, like what is a point, vector. We discussed relationship between points and vectors, and we discussed some operations on vectors, like the addition, subtraction of vectors, the dot product, cross product, and we mentioned the cosine law of vectors, which says that the dot product between two vectors v1 and v2 is equal to the cosine of the angle alpha between them times the norm of these vectors. So you can use dot product in order to find the cosine of the angle between these two vectors. Now, the sine law suggests, the sine law says that the norm of the vector, the norm of the cross product, since cross product is the result of a cross product is not a scalar, okay, so it's a vector. So we cannot say it's equal to a scalar. If we are going to use a scalar on the right hand side of this equation, we need to have a scalar on the left hand side. So vectors and scalars, they are not compatible. So we take the norm of the cross product of two vectors v1, v2 is equal to the sine of the angle between them times again the norm of the individual vectors. Okay. So taking the norm means that the norm of a vector, the distance, the length of a vector is always going to be positive, right? So therefore you can also write the same equation for v2, v1 is equal to the same thing. Okay, the difference between v1, v2 and v2, v1 are they're in opposite directions, but their lengths are the same. So you can, by using these cross product and dot product, you can find the cosine and sine of the angle between these two vectors. Now, let's talk about another geometric primitive, planes. Okay, planes in three-dimensional space. Again, when I say plane, we need to state in which space this geometric object lives in. When I say point, I need to say it's in 2D point. It's a 2D point or 3D point. Similarly, now whenever we mention a geometric object, we need to say where this geometric object lives. So lives in. So here we are going to talk about planes. To solve this problem, for example, our triangle actually is on a plane, on a three-dimensional plane. So this plane, how do you represent the plane? So we have seen that points are represented by three tuples. Vectors are represented similarly. Now, when we are going to represent a plane such as this, okay, this is this may, if you imagine this paper extends to infinity in all directions, it indicates a plane in three-dimensional space. And when we talk about planes, we also talk about a certain direction of these planes. For example, a plane divides the whole space into two half spaces, and you need to label these, distinguish these two half spaces between each other. So you may say, okay, this is the front half space, this is the back half space, which is going to indicate this plane has a front face and a back face. So how do we represent a plane? What kind of equation, or are we going to represent it as an equation or just some numbers? So how can you represent a plane in 3D space? Very good. So if we know, for example, the normal vector, the normal vector is the vector that that is perpendicular to the plane, and this vector is going to indicate the direction of the plane. And if we have a direction, for example, if you just say my plane is facing this direction, and there are infinitely many planes on this direction, so we additionally need a point to fix this plane on this line along this vector, along this direction. We need a point to fix this plane. Okay, so four numbers are going to be enough to represent a plane. Also, usually planes are represented, I mean these four numbers, in accordance with what you said. By using these four numbers, I can also derive a plane equation, meaning that this plane equation is going to be used, whether given a point, how can we check whether this point is on the plane or on the positive Hull space or on the negative Hull space. Okay, in order to check this, we need plane equation, and plane equations it's a linear equation. Okay, so this is equals 0. Describes all the points that are on this plane. A, B, C, D are constants that determine uniquely a plane. And the relationship between these constants and the normal of the plane is, yes, the normal of the plane is the vector ABC. Okay, if you are given such a plane equation, you will immediately know that the normal of this plane is going to be, so this, if the normal of the plane is going to be ABC. Now, as this equation suggests that, I mean, you can have, we didn't talk anything about, I mean, we didn't state anything about the length of this normal vector. For example, if this is my plane equation, this one denotes the same plane, right? I mean, if I multiply every constant by 2, I'm still satisfying the plane. It still defines the same plane. Okay, it's not. There is no scale of planes. Okay, the plane is something infinite. It extends in infinite directions. So, I mean, if you have somebody told you that I have these constants as my plane, but somebody else thought, oh, these constants are not correct. Actually, you need to half them by 2. You need to divide them by 2. At the end, you may find that you are talking about the same plane. So therefore, usually the general convention is that we use unit vectors to indicate normals. So in which we can, if we have found an ABC like this, we can divide this vector by its norm, by its length, to get the unit vector, unit normal vector along this, along the same direction. Now, okay, so this is all about plane equations, and simply by making this equality an inequality, either greater than or less than 0, I indicate the half plane to the front. I mean, greater than 0 are the points that are in front of the plane, and less than 0 which satisfies the inequality less than 0 are the points which are at the back of this plane. Yes, exactly. So the normal is pointing to a certain direction. So normal is pointing to the front direction. So when we say back, it's the point where the normal intersects the plane. All the Hull space behind this direction is called the back of the plane. Now, okay, maybe we can attempt to solve our line triangle intersection problem now. Since we have the plane equation, this is what we are going to need in my solution. So, okay. So before I start to write my solution, let's hear whether does anybody know how to solve this problem. How do you find xi, yi, zi? Anybody has an idea, an approach to solve this problem? Oh no, it's not. They are not guaranteed to be the angle. This makes it the angle it makes with the plane is not guaranteed to be 90 degrees. It's not a normal. It can be any arbitrary. So we are intersecting in any arbitrary direction. So the triangle is at any triangle plane in any arbitrary orientation, and we are just shooting. I mean, even we may find out at the end our line. I mean, they may not intersect at all. If our line is parallel to this plane, they may never intersect. Very good. So very good. And we can we can solve this linear system of equations. So this is the solution that I was going to tell you. So we are going to see the parametric line equation is going to help us a lot to solve this problem. And if we, knowing these 3 points, we should be, since these 3 points define a triangle, but they also define a plane. Okay, this triangle is on a plane. So if, for example, we assume a certain direction, for example, we say the plane's front direction is going to be this, we can uniquely write the plane equation given these 3 points. So we are not given any normal yet, but what we have is we can find the normal. And how? By using cross product. We know because by using these vertices, we can make ourselves vectors. Okay, the vector, for example, we can make up a vector like this by xa minus xb, ya minus yb, and za minus zb. So this is the vector v1, and I can have another vector v2, xc minus xb, yc minus yb, zc minus zb. This is my other vector v2, and you can just pick up a certain direction. It doesn't matter actually. For example, v2 cross product, if you want your normal to face towards you or towards this direction, it's difficult to draw so I didn't take a three-dimensional drawing class, so my drawing is really bad. I cannot draw three-dimensional entities on a 2D board very well, so sorry for that. So it's something like this. I mean, the way the triangle looks like, it made the normal maybe looking something like this. Maybe a short thing like this is going to indicate it. So if we do V2 cross product V1, we are going to get ourselves a normal vector, and the resulting normal vector is immediately give us the ABCs of our plane equation. After you have the ABC of your equation, the only unknown is D. How do you solve for D? By using any of these points. You can use any of them. So you have you have an equation with one unknown. Just plug in after you have the ABCs. You can plug in, for example, XC, YC, ZC. After finding ABC, you are going to after finding the normal, you know what ABC is. XC, YC, ZC is already known. The only thing unknown in this equation is D, so you know D as well. So by using cross product and one of the points, you can find the plane this triangle lies on. Now the next step is at which point this plane and this line, extension of this line segment towards this point intersect. So where do they intersect? So the suggestion that using parametric line equation is a very good suggestion. So our line, we are going to indicate our line as x is equal to x1 plus x2 minus x1 u. And y is equal to y1 plus y2 minus y1 u, and z is equal to y1 plus, z1 plus z2 minus z1 u. Okay, so this is my parametric line equation. So any point on this line should satisfy these equations, x, y, z. So all I need now is to find the u, which is going to give me xi, yi, zi. Okay, so at which u we intersect with the plane. Now, how are we going to do this? Yes, exactly. So here, the only thing, so if this x, y, z, if I'm on the plane, then all I need to do is plug in these x, y, z's into this plane equation. Okay? And instead of this x, I'm going to write x1 plus x2 minus x1 u. Okay? And similarly, I'm going to write this for y and z. And the only thing unknown in this equation will be u. Okay, so you don't, actually you're not even solving a system of linear equations. You have just one equation to solve. You don't need to apply any equation solver or anything. Okay, you just have one equation with just one unknown u. And if you can solve for u in this equation, you are going to put u in these equations, and you are going to find your x, y, z's. If this u is greater than 1, it means that your line intersects this plane. Actually, the intersection may be somewhere here. It's not guaranteed to be inside the triangle. Okay, we've just found the intersection of our line with the plane. But then after we find this point, we can just use triangle point inside-outside tests. Similar, what we did was, whether this point is on the left of each of these line segments. We can do the inside-outside test easily to see whether our line segment intersects the triangle. Okay? And if it is less than 0, it means that we intersect with this triangle is somewhere behind us. Maybe it's a triangle that we are not supposed to see in our 3D virtual world. Okay? If somebody just gave us this coordinates, maybe they gave us in an incorrect way. It's a triangle that is behind us, because this projection reference point denotes the eye of the person who is looking at the 3D world. So if the intersection occurs somewhere behind it, it means we just test the intersection with a triangle we are not seeing on our monitor. And also, another case is that this is a degeneracy. While you're trying to solve for u, you may at the end see that you cannot solve for u even in this single equation. You may end up with 0 is equal to 0. Okay? In such a case, it means that any u, maybe there is no such u. Okay, so and that degeneracy is that your line may be parallel to that plane. Okay, in that case, there is no u that is going to produce an xyz that is on this plane. Okay, if your line segment is parallel to this, and this is what happened to me actually when I was trying to give a specific example. I just gave some numbers to these and some numbers to these, and believe it or not, it turned out that the plane and the line turned out to be parallel. So I was really surprised. Oh, I couldn't find the u, so what's happening? I gave the numbers so that, they're just, for example, this was 1, 1, 1, this was just 2, 2, 2, something like that. I gave the exact scaled version as the plane, so it turned out the line was parallel to the plane. So it can happen. Okay, so this shows that if you know the geometric preliminaries and these tools, parametric line equation, plane equation, well, you can solve a problem like this really easily. And this was actually a problem, a practical problem faced by a computer gaming company in Technocamp, they were trying to solve this problem, okay, and they weren't able to find a solution to this problem by working on it maybe 1 or 2 days, but as you can see, the solution is actually not very difficult if you know the preliminaries well. Okay, any questions about this? Is it clear?
Hocam, parametric equation dışında biz bir line nasıl gösterebiliriz?
Yeah. I mean, in 2D, so the question is, you know, if we didn't use the parametric line equation, how can we represent a line? I mean, in 2D, you use the slope-intercept equation, y is equal to mx plus b. But in 3D, how would you represent a line in 3D in a single equation? I don't know the answer to that question, but we can think about the answer to that question. Any suggestions, or does anybody know the answer to that? Do we have an implicit, single equation to have all these x, y, and z's in a single equation, which is going to represent a line?
Yine bir vektör ve bir noktaya mı ihtiyacımız olacak?
For the line equation, actually, a vector is enough, right? A vector indicates, why do we, oh, no, yeah, if we have a direction, that direction can be, we can have infinitely many directions that are parallel to each other. Again, yeah, it seems we are going to need a point, so I think it's going to have some relations to this plane equation, but even on a plane, there are many lines that are in the same direction and on the plane. Maybe we may need more information. I mean, a line, when you say it's a line to me, you should immediately think about a linear equation. It has to be something like ax plus by plus cz plus d is equal to something. Or maybe the equation may be something like that. Ax plus bx plus c is equal to z. Okay, you may equate x, y, a certain, yeah, that's probably will be the case. Okay, I mean, if you have a line, it means that your points on the line, they are, for your xy coordinates, their linear relationship between each other gives the z coordinates. Okay, so the z coordinate is dependent on these xy values through some linear equation between them. So probably, I mean, the extension may be as simple as, since we had y is equal to mx plus b in 2D, it may be as simple as z is equal to ax plus bx plus z, c.
Şu denklemlerde o'yu çekersek her birinde x eksi x1 bölü x2 eksi x1 eşittir y eksi y1 bölü y2 eksi y1 eşittir z bu şekilde gösterebiliriz.
Oh, okay. So that's also a good suggestion to represent it. So yeah, I mean, we are going to have 3 equations, however, right? I mean, if we have that, we say, I mean, we can relate x and y with each other, but z is again going to be independent in this equation. It's not going to be a single equation that puts all these 3 together, is it? I mean, how can I have 3 equations here. If I just equate, if I say u is equal to this, okay, u is equal to x divided by x1 plus x2 minus x1. So what I have is, I have this relationship between them, relationship between x and y. Yeah, but what about z in this single equation? Where am I going to put z? Yeah, please. You can.
Şimdi burada o'yu çekersek
Yeah, actually I wrote it incorrectly. Yeah, it has to be. It has to be like this. Yeah. Okay, so no, I mean still, we have 2 equations here. Okay, this one is 1 equation, actually 3 equations. This is how x is related to y is related to z, and x is related to related to z. So the question is, how can we put everything in one equation? Yeah. Okay. Yeah. We can. Yeah. We can convert everything into the single equation by just summing all them, but we need to get rid of u, right? Anyway, so there is a solution possible. Okay, just you may think about this, but at the end, all these constants, okay, don't forget that x1, x2, x1, these are constants. At the end, what we are going to be finding is something like z is equal to some constant times x plus some constant times y plus some constant. Okay, so it's going to be, they are going to be linearly related. We are not going to have any quadratic or terms in this equation. Okay, any other questions or comments? So, last week, after these preliminaries, we started the convex hulls. And we indicated the convex hull of a subset of the plane. The convex hull is not, it's the general convex hull is defined for a subset of the plane in 2 dimensions. So it can be the convex hulls of spheres, convex hulls of any arbitrary shapes, or convex hulls of a set of points. So we focused on this particular problem of convex hull of a set of points, given n points. What is the convex hull of these points? And we showed that the convex hull is a convex polygon, so it has edges as straight line segments. And we talked about ON cube algorithm by looking at every pair of points, by taking every pair of points in our set, and by forming the line that passes between these 2 points, that passes through these 2 points, we find out whether all the remaining points are on one side of these pair of vertices. If it is on one side, we have shown that this edge is an edge of the convex hull. So the algorithm that we developed was something like this. Look at all the pairs of vertices and form these lines and find the edges which are going to be on the convex hull. And we did this without any order. So at the end, this algorithm gave us a set of edges of the convex hull unordered. And the post-processing step of this algorithm was going over these edge sets and try to construct an ordered set of edges in counterclockwise or clockwise direction along the convex hull. So this is an n cube algorithm, or n cube algorithm, because for every pair, which is there are n square such pairs of vertices, we check whether all the remaining n points lie on one side of this edge. And so we did in total n cube computations in this. And when we discussed the robustness of this algorithm, if we have some floating point errors, we may have missing edges on this convex hull. This algorithm, at the end, the edge set that it produces at the end may have some edges missing. So it doesn't guarantee a closed edge loop if we have some small floating point errors. I mean, sometimes if 3 points are almost collinear, one test may reveal that this point is on the left-hand side of the other, and the other test between these two may indicate, I mean, the test results we get may be contradictory if these 3 points are very close to each other and we don't have that precision to compute whether it's smaller and larger than 0. So in such cases, there may be some edges which are missing from the convex hull, and our post-processing step in which we construct the ordered edge list may crash. I mean, therefore it's not a robust algorithm. So a robust algorithm, what it should do is, even in the presence of such errors, it should produce some convex hull. Okay, that convex hull may not be the correct convex hull, but it should look close to the real convex hull. What I'm meaning is this: imagine we have 3 points which are very close to being collinear. I mean, this point here is only a tiny bit to the left of this line. Okay, so the correct convex hull is this, these two line segments. This is the correct convex hull. However, if your algorithm is able to generate the other convex hull, which has this line on to the right, it is still a convex polygon which is very close to the actual convex hull. It is not the actual convex hull. We have missed this point out, but still it is able to generate a close polygon, a convex polygon, which is very close to the, in terms of shape, to the actual convex hull. But the N-cube algorithm, it's not robust because it's not even able to generate this, the other edge. It generates something which is not even closed, okay? So it's going to miss out this edge if our checks whether the points lie to the, I mean, this edge may be completely missing, or I mean, all these three edges, maybe when we make the test, they all fail the left-right test. So at the end, our edge set may give us something like this, which tells us that the algorithm is not robust. It's not even generating a polygon. So now I'm going to talk about a more efficient algorithm which computes the convex hull in O(n) log n time, and which is more robust than this N-cube algorithm, in which it's going to be able to generate a convex shape even in the presence of floating point errors. Okay, I'm going to do this after the break, so let's have a 10-minute break.